All right. Hello, everybody. And I wanted to quickly go through my simple cleanup for the GOAP algorithm I completed yesterday in the previous video, in previous session. Uh, in previous session, I kind of mentioned that it felt kind of weird that I am collecting leaves of solutions that we find in Rust implementations that we had, and it turned out to be correct. So let me show you quickly. See, whenever I match a goal, so this is equivalent to this, I'm not pushing to leaves collection. I just remember the index of where the node resides. That's it. And I also started to keep track of whatever is the cheapest solution currently. So whenever we find a goal, we actually see is the cost of accumulated actions. If the cost is bigger, no, not bigger, smaller than whatever we had previously. So we set the cost to the new cheapest cost, and this also allows us to skip the entire sequence of code if for some reason at some point the new node that we create is becoming more expensive in terms of implementing something. So we check, okay, if the current cost of whatever node is becoming bigger, then we don't even create a node. You see, I did some shuffling of node creation. I pulled it way down before the check. So the check is, yeah, checking if we're still quite cheap. Only then do we clone the state that we currently refer to. And this is important. Previously, my state cloning happened every time when we entered the iteration. So on right on a new line of iteration, I had a freaking clone. Then I was checking against it, like immediately after that, and then I would clone it again, and there was just a huge mess of cloning, which was resulting into my code being slower, almost as slow as JavaScript code. Okay, so now I'm cloning the state actually once outside the for loop. It allows me to just check against, like temporarily borrow it here. Since we don't copy anything, don't make extra copies, then we save time. Only after that, we copy the state we had just to fill it up with post conditions, since we are allowed to. And we're checking if the goal can be finished, like if we reached the goal. And what's important, the next state can just be applied to state. I had a stupid clone thing here just because I wasn't aware of how ownership works directly, and at this point organizing the states, state usage, the next state usage here and here. I'm finally able to just dump it in here without the clone. So I'm saving extra clone sequence for this. Then I'm doing the same thing, and inside here, if we are matching a goal, we're checking, okay, is it the cheapest thing we found? Um, so yeah, here we say, okay, yeah, it is really cheaper, and we push the node here. Oh no, it's already pushed, and we just record that its existing size, like its index now is this, and we say the leaf thing, the very leaf thing that is cheapest is this index. This is an index, like optional index, and we record the cheapest dereference, the cheapest value here, and save it. With available actions, yeah, we just did whatever we did in there, and internal leaf is also a so it recursively calls the graph, and we are getting an optional index to the cheapest solution we had. And of course, if there was a cheapest solution found, considering that we did pass a cheapest price, it got mutated. I mean, yeah, it's not the cleanest way, but it works. We work directly with the variables, so we store it. If it did find something, then it updates the leaf too. Um, this is a weird implementation, but still, um, it works really, really well. So this is actually catching recursively, and we return the leaf way up. Whoop. All right. Did I break it? So yeah, let me cargo run it. In debug mode, it is slower, considerably slower than JavaScript implementation. This here is almost always at 1.2, sometimes jumps to 4. Oh wow. But JavaScript implementation is not optimized yet. Take this into account. I haven't made these kind of um, like computation savings on JavaScript side, and maybe I will make it now. That would be a good idea. Yeah, I will reverse. I will apply the same learned knowledge to JavaScript in the next session. Next session. All right, so whenever we ran our build graph thing, of course, I started out with a really expensive price initially, just so that the algorithm would try to find the cheapest solution. Yep. So this is a debug version. It's way slower, but in the release, it's actually half a millisecond most of the time. See, most of the time it's half of a millisecond. It could jump to 0.8 milliseconds, but it almost consistently is half a millisecond. So this is 500 microseconds. This is crazy fast. So what I did here was, yeah, return the index optional leaf, like optional index. I create a mutable like a reference to it, and then I just decide to again create the same list like here. So I iterate through existing nodes that we saved, and according to indexes, I'm just assembling the ID of a node, which is action name. I also pop the start node. This is a dumb decision I had at the start, but hey, it works, and it's faster than JavaScript for now. And then I reverse it because I am going from top to bottom. And the very important thing, I am now stopping the duration, like without printing anything to console. So previously I was printing stuff to console, and my measurements were not consistent because printing is expensive. So now it's computation is at least working in the same manner as JavaScript implementation. So this session is done for now, and with the next video I will try to use the same approaches I used in here, maybe not one-to-one, not with indexes, but just I will just skip maybe um, stuff where we know for sure that the implementation is going to be more expensive. So luckily we will maybe get exactly the same half a millisecond speed. Nice. See you in next session.